This is the first day of Chapter 2. We're going to cover parts of Sections 2.4, 2.5, and 2.6. This is our introduction to proofs. So a proof is a logical argument in which each statement you make is supported by a statement that is accepted as true. So we can use things such as definitions, we can use postulates and theorems that we've learned, we could use formulas, all these things that we already know to be true we can use to justify our arguments. There are three main types of proof. These are not the only types of proof, but these are the ones we will be doing in this class. So paragraph proof is more informal. It's more written how you would say the things that you're saying. So this because this. Paragraph proof is very much used in conjunction with what we call a coordinate proof. These proofs use figures in the coordinate plane and algebra to prove different geometric concepts. So you might be proving that two triangles are congruent, and you're going to explain using your words. The one we are going to primarily focus on is called a two-column proof, and it's named that because it's formed in two columns. One side of the columns are the statements, and the other side are our reasons. Those are the properties that justify each step. So we're going to ease our way into this, and we're going to start with some algebra terms that we should already be familiar with. So the addition property. If you add the same thing to both sides of an equation, that is the addition property. So it's not just adding two numbers together, but adding something to both sides, right? That is the key phrasing that they're using here to show the addition property. And then the same thing's going to be true for the remaining ones here. The subtraction property when you subtract the same thing from both sides. The multiplication property when you multiply both sides of the equation by the same thing. And then the division property when you divide both sides by the same thing, right? All of these phrases, or all of these terms, I should say, include the phrase both sides. The reflexive property. So these are a little newer. You may not have seen them before. The reflexive property is when you just say that something is equal to itself. It's almost like a reflection in the mirror. You're looking back at yourself. I don't want to call it a useless property, but it is somewhat silly, but we're going to use it sometimes before we do addition, subtraction, multiplication, or division in a non-algebraic proof, so a more geometric proof. The symmetric property is even sillier than the reflexive property and is not used nearly as often. It's when you reverse the order. So if A was equal to B originally, and in the next step you said that B equals A, that is called the symmetric property. The most common use of that is if you were solving a problem and you ended up with 3 equals x. If suddenly you wanted to write it as x equals 3 instead, that is using the symmetric property. It's symmetry. The transitive property is going to be so incredibly important. When two expressions are equal to the same expression, they are equal to each other. So if A was equal to B, and you also knew that B was equal to C, you're almost linking together the A and the C by the fact that they both equaled B in common. So I like to describe this to help people remember it as the cars of a train, for transitive, train. If you knew that A could connect to B and B could connect to C, then A is also going to be connected to C. The substitution property is when you're replacing part of an equation with its equivalent. So the difference between these two, because they are very often confused, you can only use substitution if there's an equal sign, not a congruent sign, whereas transitive can be used in both scenarios. You can link together things that are congruent, you can link together things that are equal. Substitution is you're replacing a piece of an equation. So if you had x plus y equals 12, and then you knew that x was 5, I can replace the x with a 5 in the equation using substitution. I'm replacing or substituting in. The most important thing what we need to think about with our proofs when we're using these things, transitive, I had to have seen the A before if I have it in this last step, and I had to have seen the C before if I have it in this step. Whereas substitution, I can create a brand new equation by replacing parts of an old equation. Transitive, you cannot replace the pieces, you have to replace the whole side of the equation at once. And then we have the distributive property, which I do believe we should be familiar with, right? Using the arrows to distribute. And then simplify is kind of our catch-all term for when we're combining like terms or reducing fractions. The main thing simplify is doing is it's not working on both sides of the equation. It's only affecting one side of the equation, what you're doing, right? So you could be adding terms, but you're not adding to both sides, which would have been the addition property. You're just combining the terms that already existed. So let's put these properties into use by completing a 2-column algebraic proof. And what this means is we're just going to solve this algebra problem and give our reasons, our properties for why we did everything. So instead of showing this step here, which I normally would have done to begin with, I'm going to not show steps on this side. I'm just going to write what the result would be. I'm going to number it. That was number 1. This is number 2. So if I were to actually do the math that I would be doing to solve, I would end up with negative 27x minus 36 here. And what I have used is the distributive property. So the reason this line exists is because of the distributive property. So the next thing I can do, sometimes with the algebraic proofs, it's easier to write your reason first. I'm going to combine my like terms. So I'm going to call that simplify, right? It's numbers on the same side of the equal sign that I'm combining. So 55x minus 27x is 28x. And I'm going to rewrite the rest of the equation. So after that, I want to add 36 to both sides. So that is the addition property. You can write property of equality for these, but it's also not necessary. So I do believe we're at our last step. I know I want to divide both sides by 28, so that's the division property. So x will equal negative 1. So that is how we would complete a 2-column algebraic proof. So here's one for you to try. If you'd like to pause, and the answers are posted online. For example 2, it's another 2-column algebraic proof, but you'll notice now we have 2 different equations. So this is really a system of equations. And the easiest way to solve a system of equations in the algebraic proof is, with a term we just learned, substitution. So I'm going to get one of the 2 equations, a variable isolated, and then I can use substitution to plug that into the other equation. So looking at these 2, the one that's going to be easiest to isolate is the x value, or the x variable in the first equation. So I am going to move the 3y over by adding it using the addition property. So now I have something that x is equal to, and I could take that and plug it into the other equation. So it'll be negative 4, and instead of an x, I'm going to replace the 3y minus 6 plus 4y equals negative 8, and what we just did there was substitution. I am going to ask, when you write substitution or subtraction, you don't just put SUB, because that could mean both things. So go at least one more letter on each. So substitution, I usually go SUBST, and subtraction, I usually go SUBT. And you could also write property. You don't have to. I'm fine either way. So the next thing I would do is I would normally distribute. So I'm going to use the distributive property. And if I were to distribute here, I would get negative 12y plus 24 plus 4y equals negative 8. So now I'm going to combine my like terms using simplify. So the negative 12y and the 4y combines to become negative 8y. I'm going to minus the 24, so that's subtraction. So like I said before, I'm not going to leave it SUB, subtraction property. And to solve for y, I will use the division property. But like before, I'm not done, or I shouldn't say like before, unlike before, I'm not done because all I've solved for is y so far, and I need both x and y. So what I'm going to do is I'm going to take this y equals 4, and I'm going to substitute it back into an equation. And I can go back and substitute it back into anything previously written in my proof. So I could choose to plug it in here. I could choose to plug it in here, but the easiest way to solve will be plugging it in here because x is already isolated. So I'm going to take from step 2, and instead of writing the y, I'm going to substitute in the value of y. And I can actually simplify this all at once. 3 times 4 is 12, minus 6 is 6, and we'll just call that simplify. If you wanted to separate it into 2 different simplify steps, that's fine, but you will find as we go along, if you're doing the same exact reason at the same time, you don't have to separate it into 2 steps. You can keep it together. All right, and now we are done with this one because we have solved for both x and y. Here's try 2. If you'd like to give it a try, pause. Answers are posted online. So these properties that we have learned also work on segment lengths and angle measures. And the reflexive, symmetric, and transitive properties will work with both congruent segments and angles as well as equal segments and angles. Any vocabulary word we've learned can be used in a proof. So if you wanted to go from a statement that said an angle was right angle to the next line saying that that measure equals 90 degrees, that is the definition of a right angle. So you could think, what does this term mean? And use the definition of that term in a proof. And last but not least here, this one will be used very, very often, and you're going to be a rock star at it before you know, and it's called the definition of congruence, and that's anytime you want to switch between things being congruent and things being equal. It's not always necessary to do in a proof, but since you're not allowed to say that angles are equal, you can only say angles are congruent. If I wanted to make an equation with these 2 angles, I couldn't have them in congruence anymore. They would have to be in equals. So switching from angle A is congruent to angle B to measure of angle A equals measure of angle B would be the definition of congruence. Same thing if I started with the measure of segment XY equal to the measure of segment AB. And now I wanted to say that those segments themselves are congruent. That would be the definition of congruence as well. So let's look at these and just give the reason, either property or definition, that justifies being able to make each statement. So the first one is showing that these 2 measures of these angles are equal, and it's the same exact one, like looking in a mirror right back at yourself. So that would be the reflexive property, right? See your reflection, it is the reflexive property. In the next one, we have EF equals GH, and GH equals IJ. So now EF is equal to IJ. So I have seen EF before, I have seen IJ before, and both of them happen to be equal to GH. So when I'm going to link together 2 previous statements to create a new one, that is the transitive property. And last but not least, if EF equals 8 and EF plus GH is 11, I now have 8 plus GH is 11. I used to have an equation that had addition in it. So my new equation changed the EF into an 8 because they were equal. So that is substitution. So here's try 3. You can pause it if you'd like. Answers are posted online. But that is actually the end of our first day of Chapter 2.